Hey everyone, thanks for listening in to my session on open source supply chain security today. My name is Dan Lorenc, and I'm recording this session live from Austin, Texas. I'm a software engineering lead at Google, and I'm also currently the chair of the Technical Oversight Committee for the Continuous Delivery Foundation. I've been working in and around open source software for close to a decade now, so this topic is one that really hits close to home for me and keeps me up at night. Most of my time in open source has been spent in projects related to platform as a service systems, cloud technologies, containers, and CI/CD, or continuous integration, continuous delivery systems. Most recently, I helped start the Tecton open source project, and I'm now working on an industry-wide effort to help secure the open source supply chain for everyone, both of which I'll talk about a little bit later. This is my first virtual event, and I'm hoping to have a little fun with it. We're going to do a couple quizzes and polls later on, where I want you to be interactive and answer in the chat. And please be honest with your questions. This is a judgment-free talk. So here's what I'm going to cover today. I'm going to start by covering the state of open source supply chain security. Unfortunately, it's under attack. I'll cover how, by who, and what you can do to protect yourself today. I'll also discuss what we're doing as an industry to help solve this for everyone. And then at the end, I'll finish with some links and pointers for how you can get involved to help out if you're interested. All right, before we get started, open source software is amazing, first of all. I've spent most of my career using it and building it. But we do need to face the facts as a community. Hiding the problems that we're currently facing is not a solution to solving them. I'll start by explaining one of the most terrifying and pressing problems facing open source today. And if you're not terrified by the time this session is over, please rewind and watch it again. It's one of the benefits to doing this in a pre-recorded fashion. All right, so our first interactive portion of this talk today. Let's do a quiz. I'm going to start by trying to explain the problem facing open source security and open source supply chains with a metaphor. Hopefully some people on the stream recognize these. These are USB thumb drives. Before Dropbox and Google Drive, these are how people actually used to store and transfer files between computers. Crazy, right? All right, so let's get started with a couple questions. I want you to type yes or no into chat to respond to these. All right. If you found one of these on the street, if you were just walking around and found one sitting on the ground, would you pick it up, take it inside, and plug it into your personal laptop? All right, I'm going to wait here for your answers in the chat. So please participate. Don't make me call on people individually. Okay, great. All right, question number 2. Let's pretend you were heading into your office at work and you found one of these on the sidewalk. Would you bring this into your office and plug this into a work computer? Okay, hopefully people are starting to get the theme here. All right, now one final one. Let's take this to the extreme. Let's pretend you work in a data center and you were on your way into your production data center. You found a flash drive sitting on the sidewalk outside your production data center. This sounds silly. We'll explain a little bit more later. Would you take this into your production data center and plug it into a server? Okay. One last one to wrap this up, since everybody hopefully gets the answers to these correctly. Have you received any kind of security training from any company you've worked for on what to do in one of these situations? Have you ever gone through training where they told you not to plug untrusted devices into your computers? Okay, hopefully most people have received some kind of training on this and understand why you're not supposed to do this. Never tried to do a Q&A in a recorded talk before. Hopefully that worked out well, and we can continue this throughout the talk. Thanks for playing along, hopefully. So these are silly examples. Hopefully everybody knows not to plug untrusted devices into their machines, especially inside of a production environment, because this has hopefully been hammered into us strongly by all of our security departments. This isn't silly, though. This has been an actual attack that's been used many, many times. It's even been carried out at the international level. If anybody remembers the Stuxnet worm that was used to disrupt uranium enrichment in Iran, that was allegedly carried out like this. USB flash drives were dropped near facilities in order to breach an air gap to get the Stuxnet worm into these enrichment facilities to disrupt production. And personally, I even had to run in with this once almost, and learned how seriously my company, Google, takes this threat. I was living in San Francisco back in the time, probably 2013 or 2014, and a friend of mine had just gotten a brand new drone. We went to fly it near the Bay Bridge on Embarcadero, which is right next to where the Google office is located. Drone technology was a little bit new at the time. He was a little inexperienced flying it, and a gust of wind came along while he was taking off. It sent the drone flying and got a little out of control and ended up crashing into a building across the street. He got lucky. He hit the Google building where I was working at the time. He turned out to be pretty lucky with this. I went home and got my badge and went into the office to try to look for the drone. By the time I had gotten in there, the drone had already been confiscated by our security team. They were a little bit concerned he was trying to spy on the office, but since I was an employee and vouched for him, they agreed to give him the drone back as long as he showed them the pictures on it and that he wasn't taking any pictures of the office. But, and this surprised me at the time, I hadn't even thought of this, they were smart enough to not plug in his SD card to their machine themselves. They made him go get his own laptop, plug that in, and show it to them. That's how scary plugging untrusted devices into a computer is, and that's how creative some of these attacks are, trying to get people to plug devices into their computers. I was really impressed by our security team. All right, so why am I talking about drones and uranium, and what does that have to do with open source software? Time for another quiz. This one is a little bit more open-ended. No yes, no questions here, but the same rules as before. I want you to type your guesses into the chat. What's the difference between plugging a USB flash drive that you find on the street into your laptop and typing a command like this using your favorite package manager of choice to install an open source dependency? Type your guesses into the chat here. What is the difference between these two situations? All right, my answer, only one of these runs as root in production. This is a little bit funny, but it isn't really a joke. In both of these scenarios, you're taking code or binaries you found somewhere, whether it might be the internet or on a sidewalk, and running this on a computer. The only difference is that usually npm install express or whatever package manager of your choice you want to use gets packaged up and runs alongside your code in a production environment, while the flash drive is stuck just on your work laptop. And that's kind of the theme we're getting at here. Running untrusted code, no matter how you found it, is dangerous. Here's an example of what we're looking at with the npm install express case with some numbers broken out. When you type this command, before you get started writing a Node application, you're installing 53,000 lines of code that you probably haven't looked at just to get started writing a simple Node.js app. This includes code from 37 different people. And then the transitive dependency tree here is over 126 packages just to install one package before you've written a single line of code. Again, I'm not trying to pick on NPM here, just using this one as an example. Next, we'll take a look at Go, my favorite programming language, and show how that suffers from some of the same problems. Okay, so now in this next session, I'm going to do a quick demo showing how easy it is to carry out one of these supply chain attacks and how hard it can be to spot one as an open source maintainer. For this demo, I'm going to be using a sample application I have here called Numbers CLI. This is written in the Go programming language and uses the new Go modules package management system. This basically runs a simple command line app that takes an input as a number and tells you whether it's even or odd. You go ahead and run this here. The demo gods are with me today. And we'll pass in 4 as an input. 4 is an even number, so hopefully it prints 4 is even. Excellent. It works. This is where the applause should come in for my live demo working. All right, let's try it again with an odd number just to make sure it works for both cases. I don't know about you, but this is well tested enough for me, and I'd be happy to ship this to production. Fortunately, one of my teammates doesn't like the custom logic I have here, the modulo operator. And I get it, it's been a while. If you haven't taken a computer science class, you might not remember what this percent sign does. My teammate sent a PR to use a third-party library here. It's hopefully better tested and tells us whether a number is even or odd. So let's jump over to that PR and take a look. So here's my repo on GitHub, Numbers CLI, and here's the pull request. We're going to switch over to using a library instead of our custom logic. My teammate says that this library is well tested and it should make our code easier to maintain in the long term, which, all right, I get. My custom logic here didn't have any tests to it before. Let's take a look at the diff. Here we go. See that this uses the awesome library isodd in the go.mod file. Take a look at the diff. Cool. We use that dependency instead of our own. Now, if we want to be a conscientious reviewer, we can go look at that code and check out the tests and make sure that it does work as described. So let's pull that up. Isodd. Cool. Does seem to have some tests. We can look through those. Nice test cases. Oh, it even covers 0, which I forgot to test in mine. Let's take a look at how it works. Just be extra careful. Cool. This uses another library called isEven. We're going to be really careful reviewers today and even take a look at this library to make sure that this does what it says it's going to do before we merge this code. Hop over here and look at the isEven library. Awesome. This has its own tests too. Again, it's got that 0 case we forgot about before. And it seems pretty simple. Even.isEven. This does the same modulo operator we did before. But since this one is tested and reviewed and maintained, it should be better than using our own function. All right, we're going to be really careful today and actually merge this PR locally and do some testing before we merge the branch. I'm going to go back to my editor here. I'm going to check out that use library branch. And we're going to run it again, just to make sure that we get the same results. Whoops, we can see here, this library started a crypto miner. Now my laptop might be mining crypto coins. It might have exported all my passwords. I have no idea what happened. How is that possible? We were really careful. We took a look at the third-party library that was getting added. We even looked at its dependencies to see what was happening. This just goes to show how easy it is to carry out one of these and how hard your job as an open source maintainer is if you're not reviewing all of your dependencies. And even if you are, it's very tricky. I'll give people a second here to think about how I could have done this before I give the answer and show where that crypto mining code came from. All right, let's see some guesses. If you have any guesses here, type them into the chat. Okay, now I'll show exactly what happened here and how you could have prevented this. The new Go module system doesn't vendor your dependencies. Just check them into a vendor directory by default. So it can be hard to figure out exactly which version of them you're using just by clicking around in the repositories like I did. If we do want to vendor it, which we don't necessarily need to check these in, but if we vendor it, makes it easier to review exactly what's getting used. We can type go mod vendor. This will actually download the versions from the Go module proxy and put them in our repo so we can take a look. Type that command, and now we have a vendor directory. Let's open this up. The is-odd code is still pretty simple. This just calls even.isEven again. We can even jump over to that one. Oops, VS Code isn't working right now. Awesome, so we found the even.isEven function. It's still pretty simple. Where is the crypto mining code coming in? Well, if we look through the rest of this repo, we see that there's another file hidden here, util.go. This isn't called directly. This uses the init function inside of Go to hook in some logic. This doesn't actually mine crypto. I didn't do that to myself, but it does helpfully print that. If that print line hadn't happened, then there would have been no way for me to detect this. So how did this sneak in, given that we even looked at the isEven code and couldn't find this? Let's go back to that repo. Well, it's because there can be a whole bunch of different versions of this package published, and we didn't necessarily look at the right one. Let's look through all the commits. This is the one that we're using in our dependency manager, and you can see that this added that file. To make it a little bit harder to find, this was removed in the next commit. So if you just look at the head branch of this repo, you would miss that. You can see that I removed it right after. Now, if I wanted to be even worse, I could have actually force pushed over this branch and master, deleting all records of it from GitHub. And the Go module proxy system would have still preserved that version, so my builds would have worked in the future. The point of this demo is to scare you a little bit. Now, imagine you're a maintainer of an open source project that gets dozens of pull requests a week. Some of these might be changing 1 to even hundreds of dependencies. If you're not taking the time to actually look through every single line of code of the third-party code that you're pulling in your package management system, one of these supply chain attacks could happen to you, especially if you're not reviewing the vendor directory. If you don't know exactly what code is in your system, then you have no idea if you're packaging stuff like this. Okay, now I'll summarize the supply chain attack I just demonstrated with my sample application. First, I introduced a new dependency to an open source project through a standard GitHub pull request. If you're the maintainer of any open source projects, then you're familiar with getting these from third-party contributors. This dependency I added didn't contain any malicious code itself, but it declared another dependency that did. That dependency, in turn, hid the malicious code. It was only present in one commit. Other commits were layered after that. So it was hard to find even if you were looking for it. This worked for a couple reasons that are unique to the GitHub pull request flow and the Go module package management system. First of all, code review in a GitHub pull request when you're using the Go module package management system only shows dependency metadata by default. Code is not vendored or checked into the repository, so there's no built-in way in the code review flow to see all of the vendor dependencies you're pulling in without taking that repository, merging the pull request locally, and building it yourself. This is time-consuming, and I'm willing to bet that the vast majority of open source maintainers don't do this for every pull request they merge. The Go module proxy is what actually stores the code in this system. So even though I left it up there on GitHub just for demonstration purposes, I could have deleted that commit and still had the malicious version served by the Go module proxy. Now, this is done for a whole bunch of good reasons. This makes it so that builds are reproducible, and an author deleting or renaming a repository doesn't break the build of every downstream package. But it does have the side effect of making attacks harder to find by being able to remove them from Git history. And finally, the number of dependencies in most projects in the Go ecosystem and all programming language ecosystems is growing rapidly. Even if we did have the tooling that allowed us to review this code line by line, it would be very hard for the maintainers of open source projects to be able to spend the time on that. So to sum up this problem in a language agnostic way, we really need to take code review seriously. Hopefully everyone is already doing this for first-party code. Everyone working on a team, it's pretty standard practice now to review the code that your teammates are writing. But we've somehow let open source code and third-party dependencies slip through the cracks here. In general, we hope that there are many eyes on the problem. Since we're using a trusted library, we hope that somebody else is looking at it and reviewing that code. But in general, when everyone is responsible for looking at code in an open source ecosystem, that means no one is responsible. There's no single person reviewing every library on GitHub. That would be impossible. I mean, we're just hoping that somebody else is reviewing it, or that somebody else would notice something like this and let us know. That's not a great solution to this problem. Just to show the scale of the dependency management issue for a popular open source project, this here is a snapshot of the dependency graph for Kubernetes, one of the most active repositories on GitHub today. Again, this uses the Go programming language and Go package management systems. So this graph is a printout of the Kubernetes dependency tree from a couple months ago when a snapshot was taken. We can see just the vast scale of this problem. Every single one of these nodes, you can see how deeply interlinked they are, every single one of these nodes represents a potential attack vector for the Kubernetes tree. If malicious code gets inserted into any one of these, that has a chance of making it into the Kubernetes mainline and being part of a Kubernetes release. You can imagine how terrible that would be. Kubernetes does vendor their code by default, which helps quite a bit in the review process. Over on the right side of this slide, we can see a snapshot of the vendor directory of Kubernetes. The way this works is the code is organized by the URL. So it's typically github.com/some organization name / the repository name. So this is just the top level showing the organizations. Some of the packages coming in look like they're coming from trustworthy sources like Microsoft. What about the others? I'm not trying to pick on these, but we have no idea where this code is coming from in general. It hasn't been reviewed line by line, and we don't necessarily trust the authors of this code. And even for the code that claims it's from Microsoft, we have no real way of verifying that. This isn't signed anywhere. We have no way to ensure that Microsoft released this code. This is just placed in a folder in a vendor directory that claims it was from Microsoft. Any contributors sending code in a pull request to Kubernetes could have modified this. So we have tons and tons of attack points and very bad tooling in order to catch issues like this. We really need new tools, new practices, and new systems to scale this problem to help solve it across the industry. As if 2020 couldn't get any worse. Why is this happening now? Open source has been around forever. Package management has been around forever. Why is this suddenly a problem? This is a little timeline of supply chain attacks, including some recent ones. So we've known about this type of attack for decades and decades and decades. This was first published in a paper called Reflections on Trusting Trust, which details the bootstrapping problem. Not only do you have to know the exact origin of all the code you're using, you also have to know the exact origin of all of the binaries that are used to build and transform that code. If a compiler is hacked and becomes vulnerable, that compiler can insert a backdoor in every binary it builds after that. So you might not even see it in a review of the code. This demonstrated some novel attacks where code was hidden inside of compilers and made it very, very hard to find. Much later on, we started seeing a lot more of these attacks. In 2006, a whole bunch of the repositories for operating system level package management inside of Debian and Red Hat Linux distributions poisoned. This was a credential leak, so people were able to insert packages directly into the package manager. Later on in 2010 was the Stuxnet worm that I talked about before. This used USB flash drives as a way to get into the supply chain, where there was an air gap and third-party code wasn't even being used. Later on in 2011, kernel.org, where the Linux kernel source code is hosted, was compromised. A large audit revealed that nothing serious was done, but imagine what could have happened if the Linux kernel was compromised all the way back in 2011 to today. This isn't necessarily an attack in 2016, the leftpad issue, but this does show how deeply linked the third-party package management systems can be inside of programming language communities, particularly Node.js, which tends to have a bunch of small packages that are dependent on each other rather than large packages. Leftpad was a package similar to my is-odd, is-even samples before. It just contained one function, leftpad. It added padding to the left side of a string in order to align it. This package was deleted from the npm package repository, which broke the builds of pretty much everything in the Node ecosystem because this package was a dependency of a dependency of a dependency of something that was used everywhere. The NPM package repository made some changes after that to prevent deletion outside of extreme cases. But this was one of the biggest shocks to people using third-party packages in NPM that helped kick off awareness of this issue. In 2017, there was a very serious supply chain attack called Docker 123321. Somebody set up this repository on Docker Hub, which contained a whole bunch of useful images. Things like MySQL and Tomcat were published here under Docker 123321. After these images got quite a bit of usage, largely because of the rise in popularity of Docker images, a supply chain attack was inserted into these to install a crypto miner. Now, the Go example we talked about before, it's pretty easy to look through the code if you actually want to take the time to see where this stuff is coming from. Instead of a Docker image, these are generally on the order of a gigabyte large, and they contain both plain text files and binaries. If you don't take the time to review every single piece of that binary, and realistically, how are you going to do that, then you have no idea what's inside of it. You really have to make sure you're trusting both the source code you're using, the package manager that source code is coming from, and the organization responsible for maintaining and publishing those images. There's been a whole bunch more after this. Bootstrap SaaS was another example that's not on here. And then most recently, there's another one called Webmin. Webmin is a popular web administration tool. It's used all over to administer servers easily. A backdoor was inserted into a Webmin release by compromising the build server itself. Again, even if you have full access to the source code and review it, the binaries can be compromised that you're taking. So you have to trust the organization that's publishing those binaries as well. And again, a little bit more bad news here. Sorry, hopefully 2021 is a little bit better. I really hate to add fuel to the fire, but open source supply chain attacks in 2020 aren't looking good. This is looking like the worst year on record. By any interpretation of these numbers, this is a massive problem that is only going to get worse over time. 11 million developers are using NPM each month to manage Node.js packages. There's been almost an 80% rise in supply chain attacks in 2019, and 2020 is looking worse so far. Pretty much everyone is using open source software. Surveys carried out by different groups like Black Duck, the Linux Foundation, have shown this to be true. And this isn't a trend that's declining. This is increasing. Organizations are not reducing their dependency on open source. If anything, it is increasing over time. So again, why now? Why are we only seeing these attacks? Well, it's a combination of factors. The cost per hack in software is getting lower. There are more juicier targets being published every day as people use and adopt more open source software. That means these are better targets, which is going to lead to more attacks. Open source is rising again. The greater the usage of open source, the greater the risk of open source supply chain attacks. And finally, improved general security. Hackers and attackers want to take the easiest way in. As we finally get the tooling to harden all of the other entry points and make it harder to insert backdoors, open source supply chain attacks are becoming more attractive because they're the easiest way in that's left so far. So now the scary part of this talk is over. Everyone can relax. If you need to pause here and go look at every line of your vendor code, please do so. The recording will be waiting for you. Now we'll jump to the optimistic, constructive, hopeful part of the talk. I'll talk about how you can protect yourself today, and then what we're doing about this as an industry to help protect everyone. So let's start with some simple recommendations on how you can protect yourself, your source code, and your customers today. First of all, you need to lock down your repos. Repos are where everything starts in software development. It's where your code is stored and the source of truth for all of your dependencies as well. You want to lock these down as much as possible. Limit the number of contributors and maintainers that have permission to merge things to your repositories, and do basic other protections like enabling and requiring two-factor authentication. Disable forced pushes to make it harder for people to rewrite history, and require code review so nobody can unilaterally make changes to the repository on behalf of everyone. Next, a simple way to protect yourself from attacks in your third-party dependencies is to reduce the number of your third-party dependencies. This can be a little bit painful. Using open source libraries is easy and a quick way to get started. But this always comes with a trade-off. By using these open source libraries, you're placing trust in the authors and maintainers of those. Make sure to think critically about each one of these and decide if the benefit of using it is worth the cost of potential security problems. Every dependency is an attack point. Evaluate if you really need them all. Sometimes copying a little bit of code is better than taking a dependency on the entire library. For the ones that you can't remove, you want to audit these. You want to take a careful look at them line by line to make sure there's nothing you don't want in your dependency tree. As you take updates, make sure that you're tracking those too. Once you've got a good stable footing, being able to review changes to your dependencies on a weekly or monthly basis is a lot less painful and a lot easier to do as a team. You want to review these changes and these updates just like you would first-party code. Nobody on your team can commit code without it being reviewed. So why are you trusting a stranger on the internet to be able to make changes to your code without it being reviewed? And then a final way to help here is adding observability into your CI/CD pipeline. Your continuous integration, continuous deployment system is what takes your source code all the way through to production. You want to make sure it's observable and auditable so that in the case that something does go wrong, you have enough information stored to be able to figure out how vulnerable you are and exactly what happened. For example, if you don't know exactly which versions of your source code are packaged and running in production, then you have no idea how to find out if something like this happened to you and how vulnerable you are. Imagine a CVE gets reported in a third-party dependency. Do you have the tooling to know if you've ever deployed that version of a third-party dependency? Do you have the tooling to know if that version is running in production today? If you don't have this, and you don't have your CI/CD system instrumented, then you're in a world of hurt if something like this does happen to you. All right, so hopefully you've taken these steps to protect yourself. I'm going to talk about what we're doing to help solve this as an industry to make it easier and reduce the burden on maintainers. The first piece here is identity in software development. By removing a lot of the anonymity for critical open source software and understanding who the developers are, then it's easier to place trust in these people. Today, a lot of artifacts are just signed, and we have some weak PKI infrastructure in order to know where code and binaries are coming from. But it's hard to use, and it's not enough. We're looking at this in kind of three main parts as an industry-wide solution. First of all, we need some kind of database of up-to-date identity for contributors. An anonymous person on GitHub with the default avatar should not be able to unilaterally make changes to a Linux kernel driver, for example. We need some kind of federated database here that isn't owned by any single company with up-to-date identity information, public key information, contact information for the contributors and maintainers of critical open source software. Next, we also need identity verification services for these critical maintainers. You can sign up and create a bank account on your phone by taking a picture of your ID, but you can't do that today for any kind of open source software. A whole bunch of critical infrastructure is protected by key exchange parties that haven't happened in the last 10 years. We need these services so that you can verify who you are and people can place trust in that identity beyond just any of the existing services that are around today. And then we need a whole bunch of groundwork built up to make all of this possible. We need formats and tooling to securely manage this identity metadata so that people can look it up, people's identities aren't compromised, and it's easy to sign up for and use. A couple different efforts are going on here. Signed commits in Git today are possible, but they're a little bit tricky to set up. There's some work going on inside of the core Git tooling to make this easier. Everyone already has SSH keys added to their GitHub accounts, and there's no reason you shouldn't be able to use those SSH keys to sign commits rather than having to generate separate GPG ones and manage them across machines. We're upstreaming some work to allow SSH key-based signatures into Git to make it easier and more ubiquitous to sign commits on GitHub. The next big one is two-factor auth everywhere. So many different compromises on source control systems and package management systems happen because developers are not using two-factor authentication where it's available. We're advocating for making this feature available on any source control management system and any artifact management system, and then helping flag repositories that don't use two-factor authentication. Even if you trust the maintainer of an open source package you're using, if that maintainer is not using two-factor authentication, then you're trusting the strength in their password and every other site that might ever use that password on. Today, there's no tooling to see if these maintainers are using two-factor authentication, making that visible. We really need to adopt these security practices that already exist across the industry. So once we've moved up beyond trusting the contributors and individuals involved and identity-based systems to know who they are, we need to start building tooling to trust the source code involved. And this is a whole bunch of basic questions we need to be able to answer here. If you take a binary from the internet or inside of a container image, what code went into that binary? What tooling was used to produce that binary from that code? Today, none of this is packaged with that binary, and it's impossible to figure out without a whole bunch of reverse engineering. Some efforts are going on here in the software bill of materials space, or SBOM, which are standard formats in order to describe how binaries were built and exactly what source code and libraries went into those binaries. That's useful both for auditing as well as for CVE monitoring. If you're using a tool that has a whole bunch of dependencies and a CVE is found in those dependencies, you don't know you're supposed to be watching out for that. I talked about identity before, but being able to attach information about who wrote, who built, who produced, and who is distributing a binary and source code is another huge win. Then finally, is it secure? Not all vulnerabilities are introduced intentionally. Some of them are introduced accidentally as well. By crowdsourcing reviews and publishing findings and security audits and setting up funding for all of these programs, that we can help secure things in a scalable way. Every company shouldn't necessarily need to audit every line of every dependency they're using. We should be able to do this in a collective manner. Trusting the source is a necessary but insufficient first step. You also need to trust the build process that's used to transform that source code into artifacts that get used. If you don't know who built the code, then you can't really trust that artifact, even if you know who wrote the code. This requires us to build these federated strong identity programs I mentioned before. You also need to know what toolchain was used to build that code. Even if you trust the person that built it, if you don't know which version of the compiler, which version of the build environment was used, then there could still be issues. CVEs are found in compilers all the time, these vulnerable programs. If you don't have that metadata and you can't trust that metadata about exactly what was used to build your binary, then you're still in trouble here. And finally, was the build secure? Think of all those curl pipe to bash lines and Docker files all over GitHub and Docker Hub. If you don't know what endpoints those are hitting and what's being returned from those endpoints, then you can't really trust the entire build process. There's a whole bunch of work going on to make hermetic reproducible builds easy and usable by everyone. The artifact management system is kind of the final piece here. Attacks happen all of the time where people with credentials to artifact management systems don't protect them well enough, and those get leaked, and malicious attackers are able to upload artifacts that have been compromised directly to the package manager, bypassing the CI/CD system and the source code management system altogether. So we can secure identity information for who has access to these artifact and package managers to trust who uploaded them. There are also a whole bunch of attacks on the update process. Imagine if you had a way to block an update notification or an update detection from a certain individual. Then once known CVEs are found, you can force them to stay on an older version and exploit those vulnerabilities. There are a whole bunch of systems and research going on here to help prevent these types of attacks. Network is going on in the update framework and the Notary V2 project for container images. Then tampering. Just because I uploaded an artifact and you downloaded an artifact doesn't mean it wasn't tampered with in the middle. Signatures have been around for a while, but they're not that ubiquitous, especially in a whole bunch of the language ecosystems. So we need to make it easy to sign these chains of custody so that when you get something, you know that I was the one that produced it. And again, those standard software bill of material formats are important for making sure that we know what's going into packages. Package managers are everywhere today, and new ones are appearing every day. There's also a bunch of work that we need to do to improve package managers, the state of the art for them, and get those improvements into all the new ones that are appearing for languages. Go modules, I know I picked on them a little bit before in my demo, but they have done some major improvements here. The new version selection algorithm helps prevent developers from accidentally upgrading something and picking up changes they didn't intend. And the module proxy server and transparency log make it easier to detect changes and prevent people from distributing malicious packages. This work has resulted in some cool transparency log systems, and we need to extend this to all of the language package management systems and container images out there today. And finally, as I talked about before, we need to make CVE reporting accessible and scalable for all of the language package managers out there. That was just a high-level overview of some work we need to do. I'll quickly summarize some of the other work happening. Programming languages today don't really let you apply permissions at a dependency level. Imagine the Android App Store, where an app developer has to request permissions to do things like access the network or files on your device. Imagine if you could install a package with NPM and not give it file system permissions because you don't think it needs them. That would make it a lot harder to prevent things like cryptocurrency, mining, and exporting of credentials. And then just that kind of boring general hygiene improvement work I talked about. We have two-factor auth, we know how signatures work, but people aren't using it because it's hard. We need to encourage them, teach them the importance of it, and make it as easy to use as possible. All right, so hopefully I've scared you, but then given you a little bit of hope that this is going to be all right. I'll talk about how you can get involved and why you should. Supply chain attacks are a serious problem for open source software and software in general if you're using it, so this is something you should be interested in solving. There's nothing new here. This is a standards, automation, and data problem. Nothing really is groundbreaking. We just need to do the work that we know we need to do. So if we all focus on this together, I think that we can solve it and help prevent these attacks going forward. If this is interesting to you, we're working on it in a whole bunch of different places. The Tecton CD/change repository on GitHub is a great place to jump in if you want to help work on hermetic reproducible builds and trusting build processes in general. All right. Thanks for listening to my first virtual talk, and thanks for having me at SwampUp. Here's my contact information, and feel free to reach out if you're interested in this talk or any of the things I mentioned.